Hello, and welcome to lesson 24 of this Introduction to Calculus with Wolfram U. The topic of this lesson is the definite integral. So let's begin with a brief overview of the lesson. So in the previous lesson, we talked about the Riemann sum and the limit of such a sum for a function f of x. Now, usually picked f to be positive, and if you did that, then one could interpret the sum as being the area under the curve corresponding to f. But there is a slight problem with this approach because the Riemann sum has lots of practical applications, such as finding the area under the velocity curve. So here's an example, and that's the velocity of a particle. Let's say here's a plot, and then the area under this curve can be interpreted as the total distance traveled by the particle, in this case from 0 to 5 seconds, let's say. Now the question is, what happens if f is negative? After all, the velocity of a particle can be either positive or negative depending upon its direction. So that's the question that we want to answer this lesson, and then we want to talk about some properties of the Riemann sum. So let's begin with a definition. So because we use Riemann sum so often, we have given it a special name in mathematics. It's called the definite integral. And in fact, there is also a special notation for that rather cumbersome Riemann sum. It's just called integral from a to b f of x dx. So that over there, that elongated s, is the definite integral sign with a and b, the limits at both the ends. So the s over here, like I said, is just the elongated s standing for sum. So when you find the area under a function curve from a to b, we'll say that we are integrating the function from a to b. And luckily, the Wolfram language has a very nice built-in function that integrates these functions, and it's called integrate. So integrate is the function that you'd use to compute these definite integrals. So for example, let's look at f of x equal x squared, and you want to integrate, let's say, from 0 to 1. So here's the Riemann sum and the limit, and you get back the answer 1/3, but you could just as well use the integrate symbol that's over here. So you integrate from 0 to 1 x squared, and you get back just the same answer, 1/3. So integrate is the function to use when you want to do definite integration. Now, the point is that not every function is integrable. Not every function can be integrated. And that's because the limit in the Riemann sum may not converge to a finite value. So here's an example. You have f of x equal to 1 over x, and you try and find the integral. Now notice over here I'm using the full text over here for integrate rather than the symbol. And it says over here that this integral does not converge on 0 to 1. And that's because the graph shows that in fact you have an infinity near 0, because 1 over x becomes infinite as you approach 0 from the right. Luckily, in this lesson, we'll talk about functions which can be integrated as long as you're careful. And in general, one has the property that a function is integrable if it is continuous, no breaks in the graph, or it has only a finite number of jump discontinuities. So in this case, the point is you actually have an infinite discontinuity at 0, and that's a real problem. Okay, so let's go on now to talking about functions which have a negative function value. So for example, you have the function f of x minus x, and you want to find its area. Well, the point is, because negative, what you do is you find the area from 0 to 1 as if it's a normal triangle, that's 1/2, and then you give the minus sign, and you get the answer negative 1/2. And if you use integrate, you get back just the same result, negative 1/2, for this integral. Okay, next point over here is what happens if you have a function which is both positive and negative. So let's take the sine function, And now you see what happens over here is that the function is sometimes positive and sometimes negative. So it's positive from 0 to pi and then negative from pi to 2 pi. But in this case, what you do is you add all the areas above the x-axis and then you subtract the sum of the areas below the x-axis and you get back the net area. Now in this case, of course, you have a positive area and negative area and the net area is 0. Let's check that over here with integrate and you do get back the answer 0 for this area. Okay, so on to some properties of definite integrals. So if you work out the integral from a to b of a function, then that's the negative of the area from b to a. So for example, if you work out the integral of x squared from 1 to 0, that's the negative of the area from 0 to 1. So you have a negative 1/3 over here and a positive 1/3 over there. So in particular, if a is equal to b, then you have something which is a negative itself. So the area in this case is just 0. And that makes sense because there is no area between a and a to compute. So in our particular case, if you take the integral of f from 1 to 1, then you get back 0 as expected. Okay, properties 2. And you see over here that if you have a constant function, and you find the integral from a to b, then you just get back the constant value times b minus a. If you have a sum of functions, then the integral is the sum of f integral and the g integral. And similar for difference, the integral of f minus g is the integral of f minus the integral of g. And finally, you can always pull out constants from inside the integral sign and save yourself some computation. So for the first property, for example, if you want to find the area from, let's say, 1 to 5 for the function with constant height 5, then the answer is just going to be 20. After all, you have 5 times 4, which is equal to 20. Okay, and the final set of properties is that if you have 3 points A, B, and C, and you want to work out the area from A to C, then you work out the integral from A to B, and then B to C, and you get back the area from A to C. Now, obviously, if a function is non-negative, then the area also will be non-negative. And if f is larger than g, then the integral of f will be larger than the integral of g. And one last point, that if f is kind of sandwiched between the limits m, small m, and the capital M over here, then the area for f will be sandwiched between the area of a rectangle with sides m and b minus a and a larger rectangle with sides capital M and b minus a. So here's the picture. That's the function f, and the area under f is sandwiched between the areas of those two rectangles. So that brings me to the end of this lesson. And to summarize, we have given a new name to Riemann sums. We've now called them definite integrals. And these definite integrals have many nice special properties which makes them easy to compute. The nice thing about the definite integral is it can handle functions with both positive values and negative values, and then you might get answers which are positive or negative or even 0. And we have a very nice function in the Wolfram language which does the work for you. It's called integrate, and that is a very popular, well-used function in the language. Now, in the next lesson, we'll talk about the so-called fundamental theorem of calculus, which connects the two branches of calculus, the integral calculus and differential calculus together. But before you do that, do review this lesson, go over the exercise, and be ready for the fundamental theorem of calculus. So thank you very much. I'll stop over here.